In the next section, I want to look at solutions for the range minimum query problem. We'll start with the obvious things, and then we'll look at one thing that's not completely trivial, but still fairly easy to understand. And that will also be a building block for the final solution. And that's the so-called sparse tables. Let's first think about, without spending any intelligence, what can we do for this problem to set the tone of the extremes? We can do two easy things. We can either do nothing at pre-processing or do everything in pre-processing and do virtually nothing at query time. Right? These are the two extreme things you could do. The probably easiest of the two is do nothing at pre-processing time. Be lazy up front, sounds like a very natural strategy. We don't do anything at pre-processing time, and when we then get a query, because we did nothing earlier, we have to do all the work now. So we just scan this range of the array and keep track of the minimum. That's not a complicated thing to do, but we need to scan the entire range that we're given, and the entire range could mean the entire array. So because these are worst case running times, the best you can guarantee for the query is linear time. Okay? It's clear that this is the best to do if you don't really spend time to look at the entire array during pre-processing. There's really no way to go around this. Any algorithm that spends less time at pre-processing, little O of n time at pre-processing, cannot have seen all elements of the input. So if I then ask you at query time for the entire range, it must scan the entire range again. Otherwise, I can smuggle in a minimum at a position that the algorithm hasn't looked at, and so then it wouldn't be correct. So any correct algorithm with little O of n pre-processing time needs to have this query time. Then I can also just do nothing at pre-processing if that's the same worst case, right? So it should be clear, anything to improve on this needs to spend a substantial effort during pre-processing time. Let's look at something with very substantial pre-processing time. That's the opposite. We don't want to do anything at query time, which means we just write down all solutions up front. I can do this. I can create a big matrix that has, for all combinations of I and j, the answer pre-computed in that array. I can fill this array. The array has size roughly n squared, but if I'm stupid and I just pre-compute each cell individually, I would get a linear contribution for each cell. So you have to fill n squared cells in this matrix, and each takes it's a bit of a lie. Let's say each takes linear time at most, and some of the cells, a small fraction takes linear time at least, and so the overall time is cubic. We can do a little better than that. We can do the pre-processing a little smarter, and then we get it down to at least quadratic. Would anyone like to guess how we do this? It's nothing very fancy. So we're looking at this entry mij. Let's use the picture up here. So I and j are these ranges. Now the observation is, if I, for example, know already the minimum in the range excluding the last one, there are just two options for the minimum of the bigger range. It's either whatever the minimum was in the range one smaller, or it's the single new element, right? It's just these two options. It has to be somewhere, so it's either contained in this or it's this one. So you can always use a formula like this. That's formalizing what I just said. You can take the previous value. I guess m is the index, so I should wrap this with A of A at this position. Then I can squeeze it in one line. Is one of these two options. It's either wherever the minimum was without the last one, or it's the new element. And this notation, argmin, is supposed to mean the outcome of this function is the argument where the minimum was attained. So it's either this value or j, m of ij minus 1 or j. And you apply this function this function a, look up a, and then take the argument where it was minimum. It's just a convenience to write it. Is that confusing to anyone? I could have written the same in a piece of code. I don't feel like doing it. So it's you take the two options and you check if one is smaller, you take the first, otherwise it's the other. Let's do it once. Okay, that's the same. Good. That's easy, right? So we can use this formula. If you fill the array so that the range is growing, we have to make sure we have computed the shorter ranges first. So you do an inner loop that loops over the length of the range, an outer loop that loops over the range length, and then a next loop that loops over I, and then you fill the array that way. Then you can use this formula all the way through, and then you get it in quadratic time. Now these are two valid solutions, but both quadratic pre-processing time is not really interesting, or the linear query time is not very interesting. So we want to do this a lot better. And the first attempt to improve upon this is to note that you don't really need all these entries to do something quick at query time. You can do away with a lot of the entries in this table M and still get very fast queries. Now, you will have to do something at query time if you haven't pre-computed all the answers. So we have to figure out a compromise to do a little bit of work at query time, but substantially reduce the amount of data we have to store for it. And the one solution is you still store this entry, this matrix, but you leave out most of the entries. You only store the ones where the length of the range, L, is a power of 2. So you would probably want this matrix in a different format if you want to store it in memory. You would have the first index as the starting position as before, and the second index is the exponent of the length. Okay? So it's just this translation. I mean, this would contain the same entry as mi, and then j is I plus 2 to the k minus 1. Because we want the length to be exactly 2 to the k. If you count how many entries you have, for each starting position, there can be at most log n different powers of 2 that fit below n. After you've done that many, you would overshoot the length of the array, and so that cannot be a valid entry. So n times log base 2 of n is the size of this matrix now. And so you get down from quadratic to n log n. That's a substantial improvement. Okay, so that's great. We know what we store, but we still have to answer queries, right? So it's not clear anymore if we can still do this, because we haven't stored all the queries. We haven't pre-computed all the answers. The trick is to use something like the argument before. The minimum in a range it has to lie somewhere. So if we can find two overlapping or two touching regions for which we know the minimum, we can just do the last step of comparing the values at this position, at these two minimum positions, and take whichever is the smaller. And the trick here is to say whatever range you start with, you can find a power of 2, namely like this. So it's a power of 2 that lies between the length of the range and half of the length of the range. And there always must be one, otherwise you would have left out powers of 2. So you can always find a blue one that has length power of 2 and starts at I. And you can find a green one that has the same length but ends at J. They can be overlapping, as in this example. They could also be just touching, but then you could have taken the next power of 2. So in a sense, you can make one of these two inequalities strict and it would still work. It doesn't change the algorithm at all, which way you break it. You cover this range by the blue and green positions. Some positions are double covered. Now, the minimum in this range has to lie somewhere, either in the green or in the blue region, potentially in both. So if you take the positions of the minima of the blue and green region, you can just take a comparison between those two numbers, and then you find the minimum of the overall range. Okay? That's the key idea. And this helps because the blue and green regions have a length power of 2. So they're one of these few entries that we stored in our table M prime. Specifically, these are arrangement queries of these two inputs. And so we could find these. Needs a bit more space. So where would you find the first one? It's an M prime starting at I, and the length is K. That's the easy one. And the second one we have to convert, but I've already done this here. So it's at J minus 2 to the K plus 1, and then K. Because that's the length, right? We encode the exponent of the length here. So again, if you have pre-computed all these M prime values at query time, you look up these two values. That's two indices in the array. You take the values at this position, compare them, and return whichever is the smaller one. So the same construction with this argmin that we've used before. All right? Similar to before, we can do the pre-processing time so that each entry in the matrix takes constant time to compute. And the trick here is, again, the same as before. If you want to compute this next bigger value, you know that that is a range that covers I up to I plus 2 to the K. Now if you cut that range in half, you find two ranges. This goes up to I plus 2 to the K minus 1, and then here is I plus 2 to the K. So you find two ranges that are half as long. Again, a power of 2 in length, so you have computed them already. So you can do the same trick as before. You do argmin, and you use those two ranges. So you start at I and use the one smaller. So that's supposed to be a square bracket, as is this. Oh, come on. The other is I plus 2 to the K, and also K minus 1. You can do the pre-processing so that the lengths increase, right? The outer loop is over k, the inner loop is over I. So you can make sure that these two are both known when you want to compute the next one. So it's the same trick. We cover the range with two ranges we've already computed. So you use the same trick over and over again. Minima are, in a way, you can split it over different ranges and then reduce it to the minimum of two minima. So we overall get a solution that has constant query time. That's great. And n log n pre-processing time and space. That's already quite decent. Now, the only thing that's left is to get rid of this log factor. We want to get it down to linear. Okay,